Hello, my name is Jared Skeens and welcome to the Zoom room. Today we want to look at Pure Maths 3, Integration, Part 1, the Trapezium Rule. But before we get to the Trapezium Rule, as you might have heard me say in previous videos, I want to work on training your mind before we train the skill. So we're just getting into this new unit on integration, and there's a couple of mental things that we should um, establish in our thinking first before we start diving into these various methods that we're going to look at. So the first thing that I want to point out is just a general mental map. When you get into an integration type problem, I like to look at it in 3 stages, and I call it simplify, integrate, evaluate. Most of the time, when you get into an integration type problem, there's going to be something that you need to do first, some sort of a simplification activity. It could be simple, it might be a little complex, but there's usually something that you need to do before you actually do the integration itself. So that's one thing that you want to focus on, that stage. What do I have to do to prepare it for the integration process? Then the second stage is the integrate, meaning the mechanics of actually carrying out the formula and making sure that you integrate it correctly. Then the third stage is the evaluate. Now, the evaluate might come off of the indefinite integral. Remember back in Pure Maths 1, we talked about indefinite integral, where there's no bounds of integration, and the definite integral, where there are bounds of integration. So with the indefinite integral, then you have the plus c, and there'll be information provided that will allow you to find that plus c, which is the specific solution. Or if you have bounds of integration, then you'll go ahead and calculate those bounds in the evaluate stage. So we got 3 separate stages, and you mentally want to pay attention to which stage you're in. Be careful that you don't skip a stage, but you want to think, okay, what do I do to simplify? What is the mechanics of integrating? And then how do I finish off the problem with the evaluation? Okay, so this is a general mind map to kind of help you stay organized in your process. And you'll hear me refer to that frequently in these next several videos involving integration. Now, the second mental thing that I would like to establish for you is some type recognition. When after we've covered these various methods of integration, you're going to get to a Cambridge question like in an exam. And because you have all of this information now in your head, sometimes students panic. They'll panic because one, they'll feel restricted and not know what to do, or they'll feel like, okay, I know I'm supposed to integrate, but then in their mind it becomes open-ended and there's too many choices. So we want to kind of put a little bit of parameters around your mind so that you don't feel like it's open-ended, and that you do have choices that you can think through so that you don't feel restricted. So we want you to be able to identify specifically what it is that you're to do, and then you can go through this process. So I've identified for us 6 types that you should look for. I know it's kind of a long list, but thankfully some of them are quite obvious and others are not. But these 6 things, you don't necessarily have to memorize them, but you should go through them over and over again as we go through these different videos. As you approach your questions either in your worksheets or you run into it in an exam, you want this mindset to already be there so that you can just go down that checklist in your mind and identify what specifically that you will do. So the very first thing is just your basic rule. Don't forget your basic fundamental integration rules. So it might be something, for example, in a simplify, you might have 1 over x squared. And so for the simplify part, you just might need to bring it up as x to the -2. Okay, so this would be like your simplification step. And then, of course, you'll go into the integrate part where you integrate this. But this would just be your basic algebraic rule. Is it a basic algebraic or a transcendental function like a logarithm, exponential, or trigonometric type thing? So that's what you're looking for there is, does it follow a basic rule? And by the way, all the basic rules for the algebra and the transcendental function are in your formula sheet. So start with having your formula sheet open to the integration section of your formulas and just look briefly through there. If it's not there in the list, then it's probably not a basic rule. Remember, your basic rules also come with the expanded form where the x is now a parenthesis with something in the parenthesis. But all of that should be in your formula guide, and use that as your starting point. If it's not there, then you're going to be looking for one of these other things. I can't remember if number 2 is specifically in your formula guide or not, but it's related to the transcendental function of logarithm. A logarithm, ln x, when you derive it, becomes 1 over x. So when you integrate it and go backwards, this one can be a little tricky because you're integrating a 1 over x, and it looks algebraic. And so you might think, well, to simplify, I just bring it up, and then it looks like x to the -1. Well, the problem is if you follow your basic rule, you add 1, and then you divide by the number, and you end up dividing by 0. Obviously, you can't divide by 0. So this is where you feel like you're stuck because it looks algebraic. You follow the simplify, you carry out what you think is the rule for it, but it doesn't work. So you need to say, okay, this is a fraction, and this is the first thing that you should think of. Is the numerator the derivative of the denominator? And in this case, the derivative of x is just 1. If the numerator is the derivative of the denominator, then you know it's not an algebraic rule, it's actually the logarithmic rule. So, and these can be quite expanded. For example, not just 1 over x, it can be something more complicated. Like let's say on the bottom you have x squared plus 5x plus 7. And so on the top you get 2x plus 5. So notice here you have a polynomial on the bottom and then a polynomial on top, but the top is the derivative of the bottom. Okay, so don't forget that we did cover this back in the transcendental functions when we looked at derivatives and integrals of transcendental functions. But just to review, this then, when you integrate it, would become ln of, and don't forget to use the absolute value. And let me put it down here. There's not a lot of space over there. This then would become ln of x squared plus 5x plus 7, and then plus c because there's no bounds of integration. So this form of the derivative over the function is an important one to remember, especially if you're working with fractions and you're not sure what to do. So there's only two really things here that might be confusing with fractions that don't have an obvious method that you should apply. These number 2 and number 5 are ones that you want to keep in mind regarding fractions. So that's number 2. The third one, these aren't in any particular order. You could really write them in whichever order you want. But I guess the basic rule is the one that you want to start with. And then if it's a fraction, then look for the top being the derivative of the bottom. Then number 3 is going to be a substitution method. And it's got a red dot by it because this is going to actually be our video for part 2, as we'll cover substitution. And substitution is quite obvious. You won't have to worry about this one because the Cambridge question actually tells you use a substitution. And Cambridge is quite nice on this question type because they provide for you the U equals statement. There are some curriculum that do not provide that for you. You have to look at it and determine a proper or an appropriate substitution to use. So Cambridge is quite nice in this particular type. They tell you it's a substitution and they provide for you the initial U equals statement. And then you're going to see that one of the first things that you're going to do is you're going to establish the du statement. And we'll talk about that in video part 2. Then there is a integration by parts. And we will also have a video on this. This will be the part 3 video where we'll look at integration by parts. And you're going to use that method when you have a product or a quotient. And when I talk about a quotient, I'm not talking about like the same kind of a fraction up here. What we're talking about is more like, say, you're integrating an x times cosine x. Okay, so here you have an algebraic term multiplied by a trigonometric term. Or you might have something like, let's just say, x over ln x. So here again, you have an algebraic term divided by a transcendental function. So if you have a product or a quotient of two different terms that have x in it, then that is when we're going to use integration by parts, and we'll talk about that more in depth in a different video. But for right now, I'm just listing it as something to look for in these question types. Then number 5 is maybe you have a fraction that is not in the form where the top is the derivative of the bottom. So in those cases, it still might be like a polynomial on the bottom or a top, or it could be especially maybe could be in factored form. But the point is, it doesn't fit number 2. So what you're going to look for is, can partial fractions be used? Use partial fractions to take that one big complicated fraction and break it apart into 2 or 3 simpler fractions that then you can simplify and integrate from there. So that one is something to keep in mind as well, because that can be confusing if you don't recognize it. You won't be able to know how to handle that complicated fraction. So partial fractions can be used in this simplification process. Really, most of these are in this simplification process. This one is just recognition. U substitution is a simplification. So is by parts. It's also a simplification method that prepares you to do the integrating. And then lastly, number 6 here, we have differential equations. We'll have a separate video on that. That one is fairly easy to recognize if they provide you the differential equation. If they do not, and you have to establish the differential equation, it's a little bit trickier, but we'll deal with that in video number 4. Okay, so these are the types. I know, again, it's a long list, but at least it sets some parameters for your thinking. And the more you go through this list, the more comfortable you become with it. And then you can start, you'll see in your worksheets, if you practice this thinking, then you'll find yourself being able to identify more quickly what method to use. Then you can just jump right into the method and feel confident that you're doing the right thing. So that's what we want to start with first, is establishing a few mental guides. Here's a general mind map that we're going to follow on a question by question basis. This is a recognition of what type or method that you're going to want to use. And you might say, why isn't the trapezium rule on the list? Well, technically the trapezium rule isn't really integration, it is an approximation method. So in other words, if these don't work, if you go through this whole list and none of them can work, then you might want to consider using the trapezium rule. Now, the trapezium rule, you actually aren't going to have to worry about thinking through it, because they tell you right in the problem, use the trapezium rule, just like they do with substitution. So you're not going to have to worry about should I or should I. No, they'll tell you use the trapezium rule. And so this is the one that we're actually going to start with. It's an approximation method. It's not actually an integration rule that we're following. And so we're going to use the trapezium rule. If you can't integrate, or you just don't know how to integrate it, then the trapezium rule actually uses something you've learned in basic math to help you get a very close or a good approximation value of what the integral would be. Okay, so let me set up a little bit of information for that. Okay, let's look at the concept of the trapezium rule before we jump into some of the examples. So the concept of the trapezium rule obviously has to do with the trapezium, and this is from basic math. So you should already be familiar with the way to find the area of a trapezium, and that formula is 1/2 base 1 plus base 2 times the height. In other words, you're taking the average of the base length, okay, and it's like cutting off this little piece right here and putting it over there. And so you're like finding the average of the two bases, the average length, and then multiplying it by the height. So hopefully you're already familiar with this rule here. And so we're just taking this trapezium, and what we're going to do is we're going to make a certain number of trapeziums in our graph. Now, the graphs can typically go two different ways. It can go concave up, or it can go concave down. So we'll look at both of those, and we're looking at a particular interval over which we want to find the area. Remember, the basic function of integration is area under the curve. So just like derivatives was with slope, integration is with area. So if we want to find the area under this curve, well, this curve doesn't follow a particular geometric pattern that we have a formula for. And if we can't use the other integration methods that we listed previously, then we can use the trapezium rule as an approximation. So basically what we're doing is we're just turning our graph into a trapezoid, or into several of them, trapeziums. Okay, so if we go and we can make one trapezium here. There's one trapezium. So notice with a concave up, notice that our trapezium is a little bit above the graph. So this is what we call an overestimation, an overestimation. And sometimes the question will ask you that. Overestimate. Because the trapezium is including more area than what it should. Now, if we want to make this a little bit more accurate, we can divide it up into several trapeziums. But before we do that, while we have it as one, let's look at the formula again. We have 1/2 the two bases, but now the bases, instead of being this way, they're now up and down. So here's base 1 and here's base 2, and the height is actually between here. So there's a formula for finding the height. The B minus the A, which gives you this length here, divided by N, where N is the number of intervals or the number of trapeziums that you're going to use in your diagram. Although you don't have to draw it, but mentally speaking, number of trapeziums that you're going to use. So since right now we just have one trapezium, we take B minus A, that length divided by 1, that is our height. So we'll have numbers there. Now, to find the actual value of this, then the base 1 is going to be your function of A. In other words, you plug A into your function so that you can find the height or the Y value. You need to find the Y value here, and that will give you base 1. So you evaluate the function for this number here, and then on this side, you're going to up here evaluate the function for B, and you'll get this height. So you have 1/2 the height times base 1 plus base 2. Now, what if we divide this up into 2 trapezoids? Well, we have our 2 trapeziums. So if we have 2 trapeziums and we split it right in the middle, now we have this here and this up here. Notice we have less, it's still an overestimate, but it's a little bit more accurate. The more intervals that you use, the more accurate your approximation will become. So now we have base 1. Now over here, we have base 2. And this base 2 is actually shared by both trapeziums. And then over here, now we have base 3. So when we go to calculate the height, we'll have B minus A to get this length. Now we have 2 intervals, so we would divide by 2. So now the height would just be this long here, and then you have another one this long here. So your height is your height per trapezium. So B minus A now divided by 2 because we're using 2 intervals. Notice though that one of our bases in our trapezium occurs on both trapeziums. So in the formula, this is what we get. We get the integral from A to B, that's our bounds of integration. That's the section over which we want to find the area underneath the curve. The function is the curve itself. So the function, they'll provide the equation of the curve. And so we're going to integrate it using an approximation, not actually integrating, using this approximation. So here you can see the h over 2. And now what we need to do is we're going to distribute that height to all the trapeziums. So that h over 2 will stay the same for all the intervals. And then we just want to add up all these other parts. So the y0 is your initial one. beginning one, before you even go an interval's length. Okay, so the y0 is on the y-axis. That's your f of a, your beginning point. So you're going to actually have to calculate at each of these places and plug it into the y value. So let's put numbers on here. Say instead of a and b, let's say we have 4, 0, and 4. So now this halfway point, we're going to have 4 minus 0 divided by 2. Our b minus a, 4 minus 0, divided by the number of intervals, so divided by 2. 4 divided by 2 is 2. That means each height is a length of 2. That's the height. So we would have actually 2 over 2 in this part, the height, which is 2, times the 1/2, or height divided by 2. Then we want to put in this part up here. So this would be f of 0. That would be our original y, or the y at the beginning point. Over here would be our f of 4, our function evaluated at 4. That's the end one. But the middle ones, depending on how many intervals you have, are double. That means they show up on both. So it needs to count for the first trapezium. It also needs to count again for the second trapezium, because we need to find the average line there. So we need to find the average between this one here. So we need the B2 and the B1. We also need to find the average here. So that's between the B2 and the B3. So that B2 there gets counted twice. So all the middle ones, the outside ones are only counted once, but all the middle ones are counted twice. So since right now we only have one middle one, halfway between 0 and 4 is 2. We got a lot of 2's here. We have a 2 from the 1/2. We have a 2 because this, maybe we should change it. Let's call this 6. That way we don't get confused. And that means our middle would be 3. And too many 2's there. So function of 0 is this one. Function evaluated at 6 is this one. Then the middle one is 3. And we need 2 of those. So we have 2 functions evaluated at 3. And we add those together and multiply it by our height, which is 6. Now our height is 3, because we do 6 divided by 2 intervals. So 6 minus 0 divided by 2 gives us 3. So our height divided by 2, because of this 1/2, times, and we have to add up all the bases, but the middle bases there, our bases are going vertically. Our middle bases get counted twice. Now, if you're used to the old syllabus, especially if you're a teacher, you're used to the old syllabus. In the old syllabus, this formula was in the Cambridge formula sheet. Now that we're moving into the 2020 syllabus, this formula is not in the formula sheet any longer. So you need to memorize this formula and this. It is, you should be able to deduce it from your understanding of a trapezium. Okay. Now let's look at this one over here really quick. And let's just say we divide it into 3 intervals. So if we divide it into 3 intervals, it looks like something like this, this, and this. But before we do 3, let's see what it would look like if we did just 1. If we did just 1, it would be this here, and this here, and the roof of it would be right there. Notice this is below the graph. This would be an underestimate. An underestimate, meaning the area that you get is going to be a little bit below the actual value. And again, if you, instead of one, the more intervals that you have, the more trapeziums that you use, the more accurate you will be. And so you'll see that you still get a slight underestimate, but it's not as bad as if you just used one. So usually in the Cambridge questions, they're going to ask you to use 2, 3, or 4. You know, you can expect probably 2 or 3 intervals. They probably won't do more than 4. I think 3 is probably pretty general of the number of intervals that you need to do. So I would guess 2 or 3 intervals that you'll have to do, something like this, something like this. You don't have to draw the graph, but you do need to pay attention to being able to calculate your base lengths. Okay, so if we just throw numbers on here, let's say we have from 0 to 12. So our height would be 12 minus 0. And this isn't always 0. I just happened to pick 0 as the origin there. So whatever these values are, the largest minus the smallest, we've got 3 intervals. So 12 divided by 3 is 4. So that's our height. We have 4, 4, and 4. And then the height, remember, being the height of the trapezium. So they're actually going horizontally here. Then we need the bases. So if this is 0 and 12, this is 0, 4, 8, and 12. So you need to find f of 0, f of 4, f of 8, and f of 12. Remember that the f of 0 and f of 12 will only be counted once, and the f of 4 and the f of 8 need to be counted twice, 2 times both of those. So whatever those values happen to be, so you know, whatever the function is, you just plug those in and you get your numbers, and then you plug it into here. Okay, so this is conceptually what you're doing. Let's jump into some actual Cambridge questions. Okay, let's look at our first question here. Let you look at it on screen. So notice it says use the trapezium rule. So again, you don't have to worry about actually thinking of what method to use. They're right up front. Use the trapezium rule with 3 intervals to estimate the value of the integral of 0 to 3 of this function, the absolute value of 2 to the x minus 4 dx, and it's worth 3 points, so it should only take you maybe about 4 minutes, 5 at the most to do this. So what we're going to look at here, go back to the board. Now notice there's no graph. You don't actually draw your trapeziums in the diagram. If they happen to provide a diagram, you could if you wanted to, but in this case, they don't give us a diagram, and we don't know how to actually draw this. Okay, so we're gonna just say we don't know how to draw this graph, and so we need to do this mentally instead of visually. So they told us use the trapezoid rule with 3 intervals. So the first thing we're going to do is we're going to find our height, b minus a over n. So here's the b, 3 minus a, 3 minus 0, and we have n intervals, 3 intervals. And so 3 minus 0 is 3, divided by 3 is 1. That is our height. So that means starting with 0, we're going in increments of 1, which means we start at 0, we go 1, puts us at 1, we go 1 again, puts us at 2, we go 1 again, puts us at 3. So these are our 3 trapezoids. Here's 1, here's 2, here's 3. Notice these inner ones here are shared by 2 different ones. Those are the ones that we need to double in the formula. So these are the lengths of the bases or the sides of the trapezium. So we need to calculate each one of those separately. So we plug in 0. What is our function at 0? So we plug in 0 for x. 2 to the 0 is 1. 1 minus 4 is -3. These are absolute value signs, which means it becomes +3. So absolute value means it has to be positive. Then we plug in a 1. 2 to the 1 is 2. -4 is -2. Absolute value of -2 is +2. We plug in 2. 2 squared is 4. 4 minus 4 is 0. Absolute value of 0 is still 0. Plug in 3. 2 cubed is 8. 8 minus 4 is 4. Absolute value of 4 is still 4. So now we have our values for the sides of the trapezoid or trapeziums. And so now we follow the formula h over 2. So the height is 1. Remember, it's like 1/2 times h. If you prefer to do 1/2 times h, you can do that. Same thing as h over 2. So our height is 1 divided by 2 because of the 1/2. Then we need to add up the bases. The first base and the last base are only counted once. They're only on one trapezium. The middle bases are counted twice. So 2 times the 2 and the 0. So 2 times 2 is 4, plus 4 is 8, plus 3 is 11. So we get 1/2 of 11 is 11 halves, or you can put 5.5. This is an approximation of the area under this curve from 0 to 3 on the x-axis. Okay, so that's how we do the trapezium rule. I've got a couple more practice problems for us here. Okay, let's look at our next question here. Now we have a graph to look at. It says the diagram shows a sketch of the curve y equals 3 over the square root of 9 minus x cubed for the values of x from a -1.2 to 1.2. Here you can see the slight curve there. Use the trapezium rule with 2 intervals to estimate the value of the integral, meaning find the area under this curve from 1.2 to -1.2 of our function, giving your answer correct to 2 decimal places. Then in the follow-up question, explain with reference to the diagram why the trapezium rule may be expected to give a good approximation to the true value of the integral in this particular case. So let's go back to the board. And first, let's calculate our approximation. So I've drawn the graph. You can see from 1.2 to -1.2. So, and here's the function. It says 2 intervals with an answer to 2 decimal places. So let's calculate the height first. B minus A, 1.2 minus a -1.2 divided by 2, because we're doing 2 intervals. And we get 2.4 divided by 2, which gives us an interval of 1.2, meaning we're doing -1.2 is one side, 0, and +1.2. So here are our 2 trapezoids. Okay. 2 trapezoids here, and let's calculate these bases. So this would be our base 0. This one is our base 1, which occurs for both trapezoids, and then we have base 2 here. Okay, so the base 1 is at -1.2, and if you plug that in for the x, -1.2 for the x, you can calculate it on your calculator. 3 over the square root of 9 minus x cubed. You should get 0.9159. I take it out to 4 significant figures, because usually Cambridge wants 3 significant figures. In this case, they want 2 decimal points, but they usually want 3 significant figures. So you want to do a little bit more in your work. before you get to that final answer. Then you plug in 0. So if you plug in 0, the square root of 9 is 3. 3 over 3 is 1. You can see that pretty easy. Plug in a 1.2, and you get 1.112. So then you just set it up into your formula. Height divided by 2. This is your 1/2 times the height. Our height was 1.2 times, then you put in the bases. The first base was 0.9159. Remember, you're putting in the heights here, 0.9159. The last base was 1.12. Those are only counted once. The middle one is counted twice, so 2 times 1 is there in the middle. The front and the back are counted once. So we end up here, our 1.2 divided by 2 is 0.6. All this in here adds up to 4.0279. And you multiply these together and you get 2.42 to 2 decimal places. This is our approximation. Then for the follow-up question, they say why, according to the diagram, why would this be considered a good approximation? Well, if you notice on the left, or if you notice, first of all, it's symmetrical, meaning it's the same distance on both sides, 1.2, negative 1.2, so it's symmetrical. And on the left, because it's concave down, we have an underestimate because we're going below the graph. We're lower than the graph, so we actually have an underestimate here. And then on this side, we have an overestimate because we're going from there down. Okay. So if you want to look at it this way, this one is not counting that empty space, counting below it. So it's an underestimate. This one, we went over the graph. It's an overestimate. It's symmetrical. The curve looks symmetrical as well. So since it's a little over on one side and a little under on the other side, and it's symmetrical, we can say that this should be a good approximation. Doesn't mean it's perfect, but it should be pretty close to the actual value of the area. So that's the usual type of follow-up question you'll get. It might, instead of saying like this, it might ask you, is it an overestimate or an underestimate? Okay, let's go. We'll have one more for you. Okay, let's look at the last question here. Here we have another diagram provided for us, which is y equals secant x over the interval from 0 to pi halves, although the graph doesn't reach the pi halves because there's a vertical asymptote there. Can't cross over that. Use the trapezium rule with 2 intervals to estimate the value from 0 to 1.2 secant x dx, giving your answer correct 2 decimal places. Okay, let's look at the board. Now you might say, well, we had an integral of secant, but it was an integral of secant squared is tan x. This is just secant, so we don't have the rule for this in our integral formulas. We are given a graph, and we know that it's going to 1.2, all the way to pi halves. You should note, because we're dealing with trigonometry, that the domain is given in radians. So make sure you set your calculator to radians before you start calculating things. Here is our function. So the first thing we find is the height. So 1.2 minus 0 divided by 2 intervals is 0.6. So if we're doing 0.6 starting at 1, then 0.6 will actually be right in the middle. So these are our 2 trapezoids there, 0.6 and 1.2. So those are the values we need to find for our bases. So the original base, first base is shared by both, and then the outer side there on these trapezoids. You might notice I go back and forth between trapezoids and trapezium. Trapezoid, I believe, is the American way of saying it. I'm American, and Cambridge is a British curriculum, and they use trapezium. So trapezoid, trapezium, I go back and forth. They're the same thing. And so we hear f of 0. When you plug 1 in, or sorry, when you plug 0 in, again, make sure you're in radians, that you get 1. When you plug 0.6 in, you get 1.2116. And when you plug in 1.2, you get 2.7597. By the way, you might ask how to plug these in because there's not a secant function on your calculator. What you have to do is you have to use that 1 over x key. It's 1 over x, or it might be x to the negative 1, means the same thing. And this is, remember, 1 over cosine. So you're going to use that in conjunction with cosine x to the negative 1, which flips it over. This is not the inverse function. It's not. Don't put the cosine negative 1x. That's the inverse function. It's not that one. You want to use the 1 over x for the x to negative 1. These are the same thing, depending on what calculator what your calculator has as a function or as a button. And then you, inside of that, you put the cosine x, which is when you reciprocate it, algebraically, that's your secant x. So that's how you're going to do it with your calculator. You can try with these values, and if you get these values, then that means you are doing it correctly. Again, don't forget to be in radian mode on your calculator. So then our formula, 0.6, which is the height, divided by 2, times 1 plus 2 times 1.2116 plus the 2.7597 equals 0.3 times 6.1829, which is approximately 1.85 to 2 decimal places. This is our answer for the area under the curve. Then it asks in the second part of the question as to give a reason as to whether it is an overestimate or underestimate. And so this one is an overestimate because notice these trapezoids go above the curve, meaning we're getting more area than what we're supposed to. See this section right here, we're not supposed to have. So we're getting an overestimate. This is a little bit on the high side of what it should be. Okay, so that's how we do the Cambridge questions involving the trapezium rule. And as always, thank you for joining me in the Zoom room, and hope to see you again next time.